Hearty welcome to the viewers. So happy in resuming video lecture after a break of about 2 years. So before starting, I thank the viewers for continuously viewing and encouraging me. And number of viewers, number of hours, number of subscribers, everything goes on increasing. Really happy, but I have stopped, but I'm trying to start. Now, before starting the lecture, I have been a professor for about 43 years. Now, after which, now I have started practicing as a structural consultant with the Sakti Civil and Structural Consultancy Private Limited. We have opened a Coimbatore regional office and it is located in Vadavalli, Coimbatore. So with this introduction, let me go to the lecture. So this is lecture number 128. In this lecture, we will discuss on static indeterminacy of structures. So this is a very important thing for the analysis of all types of structures by all methods. In certain methods like slope deflection method or matrix stiffness method, you have to start from kinematic and what is kinematic indeterminacy. From there only you have to start. Similarly, for matrix flexibility method, etc., you have to start. Not only that, but other structures also. Indirectly, you will be starting only with the static indeterminacy of structures. So you must know what is static indeterminacy, and not only that, it is important from say competitive examinations, interviews, etc. So very important topic, but simple topic, right? So static indeterminacy of structures, right? Now, what is static indeterminacy? We know that we have got three conditions of statics: sigma v equal to 0, that is algebraic sum of all the forces in the vertical direction equal to 0, sigma h equal to 0, and sigma m equal to 0. So this everyone knows, therefore I need not concentrate on this much, right? Now, if a structure can be completely analyzed means finding out the reactions. In the case of beams, finding out the bending moment or finding out the shear force or axial force. In the case of trusses, finding out the forces in the different members of the truss, etc., can be done with these three equations of equilibrium. It is called statically determinate structures. Now, if the conditions of statics sigma v equal to 0, sigma h equal to 0, and sigma m equal to 0 alone are not sufficient to find either the external reactions or internal forces in a structure, the structure is called statically indeterminate structure. So, what is degree of redundancy, or what is degree of indeterminacy or redundancy? Degree of redundancy or indeterminacy is the number of unknown reaction components or stresses over and above the condition equations available for the solution. Suppose if you take a propped cantilever, a propped cantilever is statically indeterminate to 1 degree. If you are able to find out the reaction at the propped end, it is a cantilever subjected to upward by downward load and upward known reaction once if it is determined. So it has got one reaction component over and above the number of equations available. So it is the number of unknown reaction components or stresses over and above the condition equations available for the solution. In the case of trusses, or generally you can say a redundant structure may have external as well as internal redundancies. External redundancy means having more number of reaction components. If the structure is resting on if a truss is resting on, I say, or continuous support, namely there are three hinges. Three hinges means there will be 6 reaction components, we got only 3 equations of equilibrium. So it is statically indeterminate to 3 degrees. We are going to come to this little later. However, internal redundant means having more number of members than those required for stability. We have got only 3 equations of equilibrium. And in the case of trusses, if the number of members required for the stability of a truss is 6, then if we provide one more member, then it will be seven members. So the structure cannot be, the structure will be internally indeterminate by 1 degree. So a structure can have external redundancy as well as internal redundancy. And how to analyze the structure, there are procedures we will discuss later. Right. Now, before proceeding about the indeterminacy of structures, we will discuss about the different types of supports. One is a hinged support. A hinged support can have vertical reaction component and a horizontal reaction component as shown. That is, it is otherwise called as a constraint. Sometimes in finding out the degree of redundancy itself, we use different formulas. In one place, we use vertical reaction plus n moments minus 2. In another place, we say number of reaction components minus equations of equilibrium. In another place, we say constraints minus 3. In another place, we say constraints minus releases minus 3, like that. Therefore, you must know, basically, we must be confident about the terms. Reaction component, here it is reaction component, hinged support can have 2. So that is, when this will not come down. It is a constraint. It will prevent the support from coming down. That is why it is called as constraint. Reaction component or constraint. Similarly, when you apply a horizontal force here, or it can take a horizontal reaction, the hinged support will not move. So for hinge, we can very well take a very simple example, the hinge in a door or hinge in a window. The hinge in a door or hinge in a window, when a shutter is fixed to the frame, the hinge will allow only rotation that will permit opening of the door or closing of the door. So we cannot move the door up, door shutter up, or door shutter in the lateral direction. That is constrained. But it is free to rotate. That is called degree of freedom, or we call it as releases. In one place we use degree of freedom. In some other formula we use releases. We must be aware. Right. Now, as far as hinged support is concerned, we have got 2 reaction components or 2 constraints and 1 release. It is free to rotate. The door hinge will allow only the rotation of the shutter. Right. Theta is allowed. Theta is allowed. Right. Now, next is that of a roller support. A roller support can take a reaction component perpendicular to the plane of rollers. Only 1 reaction component. If we apply a horizontal force, it will start moving in the direction of the rollers, in the plane of rollers. Right. Similarly, when you apply a moment, it will start rotating. It will rotate. Rotation is allowed. The movement along the plane of rollers is allowed. Only a reaction component perpendicular to the plane of rollers is possible. So number of possible reaction component is 1. Degree of freedom is 2. Free to move in the horizontal direction, free to rotate. Right. Coming to a fixed support, it can take a vertical reaction, horizontal reaction, and also a moment. So 3 reaction components are available. Degree of freedom is 0. Even rotation is not allowed. The effect of fixing is to make the end slope to be equal to 0. Right. That's about the conditions. Now, before proceeding further, this point will also be useful in the next topic, namely, suppose if an overhang is provided in a portal frame, not only portal frame, it can be in a beam also. It can be a beam also. Now, here we have discussed about the degrees of freedom of a hinge, degree of freedom of a hinge, a roller, and also a fixed support. Now, suppose if it is a free end, at the free end, a vertical displacement is permitted and also a rotation is permitted. It will have a vertical displacement and also a rotation. Now CE is shown here. C at the end E, a vertical displacement is possible and also originally it is horizontal. So after deformation, after displacement, there will be a rotation with respect to the horizontal. So delta E and theta E are permitted. That is for the free end, right? Now with this, let us take up degree of indeterminacy of some structures. Now let us take a proper cantilever. A proper cantilever is indeterminate to 1 degree. That is, 3 reaction components are possible at the fixed end and 1 reaction component is possible at the roller end. So 3 plus 1, 4 reactions are components are possible, but only we have 3 equations of equilibrium. So 4 minus 3 equal to 1. 4 minus 3 equal to 1. So only the structure is indeterminate to 1 degree. So this is for a general loading. General loading means there is an inclined reaction, inclined force, which can be resolved into vertical component and a horizontal component. When there is a horizontal component, there will be a horizontal reaction at the support. Therefore, at the left support, we have shown 3 reaction components. Right support, we have got 1 reaction component. Right. So 3 plus 1 minus 3 equal to 1. Right. Suppose if the same beam is subjected to vertical loading only, so there will not be any horizontal component of force. Therefore, when there is no horizontal component of the force, there will be no horizontal reaction. Therefore, the same formula, static indeterminacy, will be equal to 3 minus 2 equal to 1. 3 means there will be only 2 reaction components at the left support. 1 and 3 are possible. When there is no horizontal force, there will be no horizontal reaction. Only 2 reaction components are left support. 1 component at the right support. So 2 plus 1, 3 reaction components minus. There are 3 equations of equilibrium. The equation, when there is no horizontal component of the force, there will be no horizontal reaction. Therefore, the equation sigma h equals 0 will be of no use. So degree of indeterminacy is 1 only. So instead of 4 minus 3 equal to 1, it will be 3 minus 2 equal to 1. So that is. Now coming to the next one. Now 1 reaction component, but roller support, hinged support. Again, general loading. So there is an inclined force. Therefore, there will be inclined reaction. It will be possible only at the hinged support. Roller supports cannot take any horizontal reaction. So horizontal reactions cannot be applied at the roller support, only in the hinged support. This is these minor things are to be carefully attended, right? So there are 4 reaction components, 3 equations of equilibrium. Therefore, 4 minus 3 equal to 1. And now here coming to this, suppose if it is subjected to general loading, because then only horizontal reaction will be possible, right? So 1 plus 1, 2, 3, 4, 5, 6. All these are roller supports. So 6 reaction components. We have 3 equations of equilibrium. 6 minus 3 equal to 3. Coming to this, again general loading. Therefore, horizontal reaction possible. So 3 plus 2 plus 1, 6. 6 minus 3 equal to 3. Now, there is another formula. Now, here we have got the degree of indeterminacy as number of reaction components minus the number of equilibrium equations available for the solution. There is another formula. If beams are subjected to only vertical loading, then we can say static indeterminacy equal to vertical reactions plus end moments minus 2. But so suppose if you take a fixed beam, we have got two reaction components in the vertical direction, two end moments. We know there will be end moment and a fixed end. The effect of fixing is to make the end slope to be equal to 0, right, vertical forces. So two vertical reactions plus two end moments minus 2. Minus 2 stands for the equilibrium equations, sigma v equals 0. Now there is no need for the equation sigma h equals 0 will be of no use when there is no horizontal component of the force. Therefore, only two equations, sigma v equals 0 and sigma m equal to 0. So this 2 stands for the two equilibrium equations, effectively useful. Right. 2 plus 2 minus 2 equal to 2. Right. So that is what is shown here. Now this beam is also subjected to only vertical loading, propped cantilever. As we have discussed, here there is no horizontal reaction, vertical reaction plus end moment plus one more vertical reaction. So two vertical reactions plus one end moment at the left support, because right support cannot take any moment. A hinged support or a roller support cannot take any moment. Therefore, 1. So 2 plus 1 minus 2 equal to 1. The degree of indeterminacy of a propped cantilever, whether it is subjected to inclined loading or general loading or vertical loading, is always 1. Because these questions will be attractive for the interviewers or competitive examinations. What is the degree of static indeterminacy of a fixed beam? If it is generally asked, you have to be very careful. We are going to prove it only after this. The static indeterminacy of a propped cantilever is 1, whether it is subjected to general loading or subjected to vertical loading only. Whereas in the case of a fixed beam, if it is subjected to general loading, namely inclined all loads, inclined loading, etc., the degree of indeterminacy will be 3. When it is subjected to only vertical loading, it is 2. So you must be able to specifically answer the question, because here we have discussed static indeterminacy equal to 2, because it is subjected to vertical loading only. Subsequently, we are going to discuss for a general loading, it will be 3. So these points are to be carefully answered, whether it is in a competitive examination or in the interview. You have to be very specific, right? So 3 vertical reactions, because no inclined force, therefore no horizontal reaction. So 3 vertical reactions. Formula is, when beams are subjected to only vertical loading, it is the vertical reactions plus end moments minus 2. 3 vertical reactions, no end moments, roller support, and here also it is roller support, minus 2 equal to 1. Right. So here you got it is subjected to, let us assume that it is subjected to only vertical loads. Only vertical loads means 5 vertical reactions plus no end moment minus 2 equations of equilibrium, sigma v equals 0 and sigma m equal to 0, right, equal to 3. This is the degree of static indeterminacy. Now this is what I told you. When a fixed beam is subjected to general loading, there will be horizontal reaction at both ends. So there will be 3 reaction components at either ends. So here you cannot make use of the formula vertical reactions plus end moments minus 2. Vertical reactions plus end moments minus 2 is applicable only for beams subjected to vertical loading only. So here there are 6 reaction components minus 3 equations of equilibrium. So 6 minus 3 equal to 3. 6 minus 3 equal to 3. That is about the degree of indeterminacy of a fixed beam subjected to general loading. Next, we will take up frames, portal frames. Now, portal frames, here again we got 2 methods. One is that is not only 2 methods. There is one more method we will discuss later. Right. So 3 reaction components at the fixed end, subjected to general loading, right? And 1 reaction component the right support. Because why I'm saying this is, sometimes there are some specific cases which we will discuss later. in some of the structures there will not be any horizontal reaction component. We are discussing about general loading, right? So 3 reaction components, here 1 reaction component. So there are 4 reaction components. We got 3 equations of equilibrium minus 1. Now this is again a portal frame. Now here it is, one end is fixed, the other end is on rollers. Here the other end is free. So there are 3 reaction components. We have 3 equations of equilibrium. Therefore 3 minus 3 equal to 0. That means the structure is statically determinate. You will be able to analyze the structure only by using the 3 equations of equilibrium, right? Now this another portal frame. Fixed means you can consider this as a loop equivalent to these two together, right? Fixed. So it is considered as a loop. Why I am using the term loop, subsequently we will discuss. So 3 plus 3, 6 reaction components. We have got 3 equations of equilibrium. So the indeterminacy equal to 6 minus 3 equal to 3. Equal to 3. Right. I have used the term loop. Now here it is applicable. Static indeterminacy for rigid jointed portal frames. The degree of static indeterminacy can also be obtained using the formula static indeterminacy equal to number of closed loops into 3 minus number of releases. So number of closed loop here is 1. This is 1. But here it is a hinged support, it is a roller support. We are going to discuss about releases. Now here it is fixed. Here here it is hinged, fixed. Most problem, right? So 1, 2, 3, 1, 2, 3, fixed. Now no release here. You know what is a release, right? No release here. Therefore, this is indeterminate to 3 degrees. Now coming to this frame, it is again a closed loop. Here it is free to rotate. A hinge is free to rotate. There is a release. Now here it is a roller. It is free to move in the horizontal direction and also it is free to rotate. So 1 release at the left support, 2 releases at the right support. So 1 into 3, number of closed loop is 1 into 3 minus 1 release at the left support minus 2 releases at the right support equal to 0. So this structure is statically determinate. Coming to this frame consists of 2 closed loops. So 2 into 3, number of closed loops into 3 minus number of releases. Now here it is free to rotate. It's a hinged support. Minus 1 equal to 5. So that is about right. Now coming to this frame, there are 5 loops. 1, 2, 3, 4 and 5 loops. So number of closed loop is 5 into 3 minus number of releases. Here there is 1 release in a hinged support. Now here it is 2. So 1 plus 2, 3. There are 3 releases. So number of closed loops into 3 minus number of releases equal to 12. So this structure is statically indeterminate to 12 degrees. Now here this need not be discussed now here, but however, suppose there is a member AC. We are going to apply this later. AC. Now suppose if you give a cut at the point at the section B, at a section B. Now as it is at B, we can apply a horizontal force as a truss member or beam member. We can apply a horizontal force. It is capable of taking. We can apply a shear force. So 1 kilonewton in the upward direction, 1 kilonewton in the downward direction. That is, it will take as it is. Right, because it is a part of P. Right. Similarly, we can apply a moment. You can apply a moment. You will have the same rotation at both ends. So it is capable of taking axial force, shear force, and bending moment. Now, how to release them? How to release the capacity of taking a vertical force, horizontal force, etc. We will discuss subsequently. Now, when you just give a cut here, right? Now, it will become two members, AB and BC. So at B, now we cannot apply an axial force as before. Similarly, as two members, it cannot take a shear force. Similarly, cannot take any moment. It will start rotating. Where moment is applied, it will start independently rotating. This we are going to discuss an analogy called tree analogy later. There, everywhere, we will be giving three releases, minus 3, like that. What is the meaning of minus 3? You will understand later only if you know this concept, right? Now, the discussion on this, right? Now, here, another point. Suppose there is a propped cantilever when it is loaded. The deflected curve will be a continuous curve. So, now here, at any point, we can draw tangents, right? The tangent will be continuous. If you draw it will be a continuous line. The tangent will be a continuous line. The same point, suppose if you introduce it, now here, this is the one. It will be a straight line. Suppose if you want to draw a tangent at this point, it will be an inclined line, single line. Whereas when a hinge is introduced at this point, right? Now, when you draw a tangent to this curve, it will be like this. When you draw a tangent to this curve, it will be like this. There will be two tangents. So here, it will be a release. It is a moment release. What is a moment release also we will discuss later. It is a moment release. So, if you know, we know that the propped cantilever is statically indicated by 1 degree. After the introduction of this hinge, it will give one moment release. It will be a determinate structure. That we will discuss later. This is the formula I told you. Static indeterminacy equal to constraints minus 3. So earlier we have discussed it is the number of reaction components minus 3. The same it is used as a, because if you come across in some book, you need not get confused what is a constraint. And here another point, constraints, this is for number of reaction components. This is releases. Constraints minus releases minus 3. Minus 3 is the number of equilibrium equations available. Now, what is a release? What is a constraint? We will discuss now. Right. Now, suppose we take a beam like this, continuous beam like this. Now, there are 1, 2, 3, 4, 5 reaction components. 5 reaction components is mentioned as 5 constraints here. 5 constraints. Right. Now, here, this will reduce the degree of indeterminacy by 1. A moment release at some point in a beam. Another moment release, a hinge cannot take any moment, right? A hinge will only rotate, right? It is allowed to rotate, right? So there are 2 releases here. That is what is called a release. So 5 constraints minus 2 releases minus 3 equal to 0. So this structure, even though it is a 3-span continuous beam, because of these releases, it is determinate. It is a statically determinate structure. Now coming to a fixed beam subjected to general loading. We know when it is subject to general loading, we know that it is statically indeterminate to 3 degrees. But we introduce a hinge here. And the hinge is introduced here. 6 is a constraint or number of reaction components. Minus 1 release. Minus 3 equations of equilibrium equal to 2. So the degree of indeterminacy gets reduced by 1. If you introduce one more hinge at some other point, that will reduce the value by one more. Namely, the static indeterminacy will be 1 only. Like that. So that is what is explained here. If horizontal forces are absent in the same fixed beam, if horizontal forces are absent, the reaction C2 and the C5 will not be there. Right? There will be only 4 constraints, 4 reaction components, minus there is one release, minus there are 2 useful equations of it. Sigma h equals 0 will be of no use. Minus 1. Minus 1. Therefore, a fixed beam subjected to general loading with a hinge in between is indeterminate to 2 degrees. A fixed beam subjected to only vertical loading will be statically, and vertical loading and with a hinge in between equal to 1. The degree of indeterminacy equal to 1. So that will be enough for beams and a frame. Next we have to discuss pin jointed frames. So pin jointed frames we will continue in the next lecture. Let us avoid a lengthy lecture. Already it is a lengthy lecture only. Anyway, so once again, I thank all the viewers for the opportunity to resume video lecturing, and thank you for your patience. Thank you all. Thank you.